So in this talk, I'm going to show you how to build distributed stateful applications on programmable switches. And this is a joint work with our partners at Microsoft and the Open University of Israel. So today, networks employ programmable data plane switches that are capable of executing stateful operations on packets. And many researchers have leveraged this capability of the switch to build sophisticated in-switch accelerators, such as load balancers and network monitoring applications. However, all of these are designed to run on a single switch. But to be practical, network functions must be built with multiple switches in mind due to the following reasons: scalability and availability, of course, but also, and most importantly, locality, which is not always guaranteed. To better understand why locality is important, we can consider the following example where we have a DDoS detector. So this implementation uses a data sketch, and when a packet comes in, we first update the sketch, and then we use the frequency estimation from the sketch to decide whether to drop or forward the packet. Now, this is only one example of applications that monitor network changes and then react to them. And in this work, we are particularly interested in such applications. So when we run this application on a single switch, everything works as expected because we have locality. However, when we distribute the applications to run on multiple switches, locality is not guaranteed. Because, for example, the attacker can use multiple flows that will be processed on different switches, and then the switches won't detect the attack. So in order to detect the attack, we need to construct a global form of the network state. And one common practice to do that is by using a centralized controller. So the controller can collect the sketches and then aggregate them. And in case of an attack, it can install blocking rules to the switches. However, this common practice has a major limitation, which is the mismatch between the performance of the data plane and the control plane. So inevitably, the controller is going to miss state changes. And in extreme cases where the attack is very short in time, it's not even going to be able to detect it. So as a result of this performance gap, many researchers have tried to optimize this communication channel between the data plane and control plane. However, these existing solutions are very ad hoc and they cannot be generalized. So in this work, we are trying to answer the following question. Can we run these distributed applications without relying on a centralized controller? And the answer is yes. As I'll show you, sketches can be replicated directly in the data plane with a provably correct replication protocol. And not only is data plane replication feasible, it is also performant. And we hope that this new tool will open the door to rethinking how the next reactive applications will look like. So I hope that I convince you that data plane replication is interesting. And in the rest of this talk, I'm going to explain to you how to implement that efficiently on a switch and also share some experimental results with you. So Swish provides a set of APIs to application developers. And these APIs expose 3 different types of shared variables that differ in consistency, in performance, and also in the implementation complexity. Now, each variable is replicated using a different replication protocol, and as a result, each switch operates on a global view of the state, which can be viewed as if one big switch processes all the traffic in the network. So we analyzed the consistency requirements of many network functions and built 3 different protocols. The first is strong grid optimized, which offers strong consistency, and we use it to build a network address translator. The second is eventual write optimized that provides eventual consistency, and we used it to build a rate limiter. And finally, strong delay writes protocol that is suited for sketch replication, and we are going to focus on this protocol in this talk, and you can obviously find details on the other two in the paper. So there are many challenges when realizing SDW on a switch, but I'm going to focus on the following two. The first is what is the correct consistency that is required for replicating sketches, and the second is how to deal with packet drops. Now, trade-off of consistency and performance is well understood, but I'd like to put some context on what it means in our scenario. So our goal is to have reactive applications in the switch that make the same decisions based on the sketch values. So in our context, consistency means how far off can two sketches be and still have the same decision made by every switch in the replica group. And we also assume that each and every packet is going to mutate the sketch. So in terms of performance, we care about how efficiently can a protocol be to accommodate this high volume of traffic. So we can take a look at one extreme of eventual consistency or reconsistency, and this can be implemented easily by simply broadcasting updates upon state changes. So while it's easy to implement, it has two major limitations. First one is that it has a high bandwidth overhead because we eagerly send out updates. And the second limitation is that due to packet drops and reordering in the network, sketches can be quite different at each replica for long periods of time, and then the switches won't make similar decisions. On the other end of the spectrum, we have strong consistency, and this can be implemented by running a chain replication protocol between the switches. While this consistency will eliminate the inconsistent decisions, it does bring nuance to the table. Since strong consistency is expensive to implement, it has high replication latency, and also it limits the concurrent operations on the sketch. So in Swish, we provide strong delayed writes as a middle ground between these two extremes, and SDW provides consistent snapshots of the sketch to each replica. It also provides a consistency known as RELAX strong linearizability, which basically means that every sketch operation can miss up to R operations that precedes it. We prove the correctness of the protocol in the paper, and we also show that SDW has low latency, and it can be as fast as a few microseconds to replicate a sketch. It also decouples the amount of communication that is required for replication from the number of updates that occur in each switch. And this consistency guarantee also allows us to provide precise error bounds for the sketches. So how does it work? Each switch maintains 3 copies of the sketch: a read copy, a write copy, and a sync copy. And when a packet comes in, it can read and write directly to the appropriate copies locally. Now, SDW operates in rounds, and in each round, each switch is going to send its sync copy to other switches. So when a switch receives an update, it merges the update with its local state. And when a switch receives all the updates from a particular switch, it can then respond by sending it a NAC. And this is important because if update packets are going to get dropped in the network, we can easily recognize that by detecting that a NAC was not received in a timely fashion. So in that case, the switch will have to retransmit the update packets. And the common solution to do that is by implementing some reliable delivery layer over the unreliable network. So in switches, the most straightforward thing to do is to buffer these update packets in the network, in the switch, sorry. So we recirculate the packets in the switch, and then we can retransmit them if needed. However, this method is very expensive because it consumes internal switch bandwidth, and it is also tricky to get right because these packets may get dropped inside the switch if there is congestion. So in Switch, we take a different approach, and we are trying to reconstruct the updates and send them if necessary. So we program the packet generator of the switch to periodically generate an ACK packet that checks if a retransmission is necessary. And if so, it generates a new batch of updates that can read the values from the sync copy and then send them to other switches. However, since we also merge updates from other switches to this sync copy, we need to keep the old values of the sync register in a separate copy. In addition, each switch monitors the number of updates and ACKs that it receives, and when it receives all the updates and ACKs from other switches, it can then advance its round. And advancing the round means that we swap the registers, and when all the switches advance the window ID to number 1, then they all read the same snapshot or version of the sketch. Another challenge in this protocol is how to implement this register swapping efficiently in the data plane, and we leverage the capability of Tofino switches to store a pair of 32-bit values, which is very efficient in terms of in-switch resources, and you can see more details about this technique in the paper. In the paper, you will also find our theoretical proof and analysis of the SDW protocol, as well as more information on recovery and the other protocols that I couldn't cover today. So for evaluation, we implemented 3 different real-world applications: a NAT, a rate limiter, and DDoS detector. And in this talk, I'll focus on the DDoS detector, but you can get more details in the paper. So we built the following testbed that includes 2 switches, and we leveraged the folded pipeline design where we can run different applications on each pipe. So we built an ECMP application, run it on pipe number 1, and then the NF, the DDoS detector, will run it on pipe number 0 in each switch. And the switches are connected to each other, as well as to 2 client NICs and the centralized controller. So in the DDoS or super spreader detector, we have an attacker that sends malicious packets from NIC number 1, and the traffic is evenly distributed because of the ECMP layer between the 2 NF instances. And we program the application to block sources that communicate with more than 1K different destinations. So the attacker sends 10K packets with the same source IP to different destination IPs on NIC 1, and then we measure how many packets we receive on NIC number 2. So we have 2 different baselines. One is the push design, in which each NF instance is programmed to send out an update to the controller in case it detects a source that communicates with more than 500 different destinations. And then once the controller receives 2 updates for the same source, it can then install the appropriate blocking rules on each switch. In the pull design, instead of sending an update, each switch can append a candidate IP to block to a local register, which the controller periodically queries. And if it sees the same candidate IP in both registers, then it can install the appropriate blocking rules. And finally, we have the data plane only design, in which switches are going to make decisions to whether forward or drop the packet based on the values of the sketch. and the sketch is going to be replicated using SDW without the use of a centralized controller. So in this graph, you can see on the y-axis the ratio of received to send packets, and on the x-axis the number of different sources that the attacker uses per second. And as we go up in the y-axis, more packets are able to go through the system, which is bad. And on the x-axis, as we go to the right, there are more sources for the controller to process. So ideally, you would like to have a ratio of 10% because the first 1K packets do not trigger the detector. So as you can see here, SDW performs ideally, regardless of the number of different sources that the attacker uses. While on the other end, the push design breaks at 1.5K different sources because it starts dropping packets, and then there are IPs that are never blocked. Similarly, the pull design breaks at 2K sources, and there the controller lags behind, so it basically processes IPs that will not be reused anymore, while the attacker is now working with a new set of IPs. So it always misses the new IPs. So to conclude this talk, data plane replication is essential for this kind of reactive applications, and Swish provides a set of APIs that developers can use to build complex and sophisticated distributed systems. In particular, we have the SDW protocol, which is provably correct. And finally, Swish is practical, performant, and fault-tolerant, and we hope that this work will open the door to rethinking how the next distributed applications on programmable switches will look like. Thank you, and I'm happy to take questions.